Please welcome to the stage Pankaj Sharma and Rev Lebaredian.
Well, hello. So good to be back. I'm glad you guys made it. You know, this is one place where you have to go all the circles to find where you're actually going to go, right? So thank you for coming back. And it's our pleasure, both of us. I don't think we need introductions. We did introductions. But what I'm going to do is to start with Rev. I think everybody knows who you are. But just tell this group a little bit, before we go deep into these questions, about a little bit about your background and you know, some of the things you've done in your career.
Well, I've been at NVIDIA for a little bit. I've been here for 24 years. Previous to that, in my past life, I worked in visual effects in Hollywood, writing software to generate the images of representing fantasy worlds that you'd see in movies and CG-generated films. I joined NVIDIA 24 years ago to bring that same technology to in interactive experiences, to video games. To take what used to take hours and hours to calculate per image, per frame, and make it calculate the same thing in milliseconds. About 10 years ago or so, once we understood what was happening with AI, that this was going to be big, we came to the conclusion that the most important application of artificial intelligence, the new algorithms we're going to create with AI, was going to be about the physical world. Applying AI and computing to the physical world, essentially robotics, things, technology about manipulating and understanding atoms and the stuff around us. And so we made the decision to take all of the tech we had built to simulate fantastical worlds, fantasy worlds, for movies and video games, and instead apply it to the physical world as accurately as possible to create a playground where AIs can learn about the physical world, that we can train them in there and test them in there before we deploy them out into the real world. So we call this Omniverse. That's what I lead at NVIDIA, Omniverse and simulation. And that's why I'm here today with all of you.
Thank you. Thank you. This is so interesting when you make the connection between the sort of fantasy world, bringing into what we are all experiencing as AI today, in like all walks of life. You know, like we were sharing examples earlier about medical science, about education. It's everywhere, right? So you started to answer actually my next question also a little bit. What I wanted to ask you was, when you think about now the company, NVIDIA, and that's such an impressive history of the company, technology leadership, shaping the whole industry, you know, the foundation layer of the whole industry. Tell us a bit more about the NVIDIA journey.
Yeah, I think most of you have now heard about NVIDIA, and you probably even know how to pronounce it correctly. This is a recent innovation. For most of the time I've been at NVIDIA, most people didn't know about it unless you were either into video games or hardcore computer science and hardcore computing. You probably didn't know us. But since the ChatGPT moment, everybody now knows about us. It seems like we just popped up overnight, that we maybe got lucky. But it was about 30 years of overnight. It took us a long time to get to the point where the world could discover what we were doing. From the very inception of the company, the idea behind it, the mission, was to create a place where the very best of the world's computer scientists come to do their life's work. That's the core mission. It's not for a specific product or a specific technology, but just the place where computer scientists come to do the very best. And the first problem we chose to tackle, our goal is to build special computers that solve problems that are near impossible And the first problem we chose was computer graphics. It was what's called rendering. It's a type of physics simulation where we simulate the physics of how light interacts with matter in order to produce those images. And we decided to do that for video games because that was a potentially large enough market to sustain the R&D that we could contribute. But the idea was that this type of physics simulation is such a large computing problem, no normal computers could do that. And if we could go solve this well enough, we could then extend that same computing to other types of simulations, to other large computing problems. And that's what we did. We made our GPUs over time more programmable, and we expanded from doing rendering to doing other kinds of physics simulations, computational fluid dynamics, molecular dynamics, seismic analysis, et cetera, et cetera. And we waited for many years for a killer app to show up on this computing platform we were building, which is essentially supercomputers that could fit under your desk or fit inside your laptop. It took longer than we thought. We introduced a platform called CUDA, which is our general purpose programming interface for our GPUs in 2006. It took about 7 years before the moment happened where finally somebody figured out what to do with all this computing power. And that was when AlexNet in the ImageNet competition was created. Some of you might know this was the big bang moment for AI when deep learning came into the scene. At the University of Toronto, 2 graduate students and their professor, Ilya Sutskever, Alex Krizhevsky, and their professor Jeff Hinton, the godfather of AI, took this old idea of neural networks, which had existed since the 1950s, I think the first idea behind it, and solved a problem that had vexed computer scientists since the 1950s. The basic problem of understanding what's inside an image to classify it, we'd been trying to do forever, and no human had devised an algorithm that could actually do that reliably.
Wow.
But using this new method, we were able to do it. We could do image classification. So we saw this and said, finally, somebody's figured out something useful to do with all this computing power. And this is a big deal, because image classification itself is an important problem. And you can imagine the same technique could be applied to other types of computer vision. But what we understood early on was that this was much more than just solving a particular class of algorithms, a particular class of problems. It was a whole new form of computing. It was a whole new form of software development. Up until that moment in time, the best algorithms, the best software was all developed one way. You just get a really smart human who knows how to program a computer. They imagine an algorithm, transcribe it into a computer as code, compile it, and you're done. And you can do it on a relatively small computer. But what we did here was fundamentally different. Instead of writing the function directly, devising the algorithm, we gave a supercomputer a large number of examples of what we would like the software to do. We gave it examples of images along with their labels, like flashcards, saying this is a cat, this is a dog, this is a tractor, this is an airplane, and we did that enough times. If you do it enough times, it wrote the software for us. And the key ingredients to that were essentially enough examples. You have to have the data behind this to feed into this machine, and a very large computer. So we came to the conclusion this was going to change everything. There's a large set of computing problems that nobody would have even dared try to go solve in our lifetimes, and now those had been unlocked. Yep. All we need is really large computers and lots and lots of that, and we need a large amount of data. And so that's where we are today. We started building the infrastructure, the blueprint for how to build these large computers, and building these supercomputers, which used to be exquisite, bespoke machines that were custom designed for supercomputing labs at national labs. They take many, many years to design. We're essentially mass producing them today because we set about scaling from a chip to systems to racks to full data centers to make a computer that scale. So this is where we are today. And the next step is going to be taking all of the stuff we're doing in AI in the realm of knowledge and knowledge work. Largely, anybody that's using AI here today is using it to make sense of the information that you have on the internet, to make sense of your documents, to make sense of things that are already digital, which is just information. But the next step is going to be taking that same capability and applying it to the physical world.
Exactly.
That's why we have so much work together with Schneider Electric. NVIDIA is a computing company. We deal with the digital world, but we need to connect into the physical world, in order to really bring the value of this technology. And this is a key partnership for that.
And we'll double click on that in a little bit, but it's so interesting what you shared, because all of us somehow take it for granted, the way we are exposed to the advantages and efficiencies brought about by AI. But bringing us back into the story, I'm pretty sure it's helpful for everybody to understand. It's not like a name which, like you said, appeared suddenly. It's almost 30 years of work, which has now gone into this huge transformation, and what were the details of how it all happened. So very interesting, and thank you for sharing. Now, if you remember, I shared a little bit with you about who all are here in the room. So this is what we call like an ecosystem. You know, there are customers, our partners, our suppliers. It's a whole ecosystem. Now, when you think about NVIDIA's huge transformation, and then when we start talking about the vision and opportunity of generative AI and the AI factories, what does it mean for us, this ecosystem? If you'd like to maybe speak to that a bit, Rev.
Earlier in the plenary, during the keynotes, the term AI factory was thrown around in there. And I think even for those that know what that is, it is kind of a weird way to describe it. You know, most people don't think of factories being these racks of computers. Like how are these two things connected? But we chose that terminology explicitly for a good reason. These AI factories, to the untrained eye, might look like a normal data center. And we still kind of use that term, data center. But a data center, as the word says, it's about data. It's about moving data around and storing data.
Yep.
The physical analogy to that would be like a warehouse. This is where you store your goods, and you can maybe move them around in your logistics supply chain. It's essentially what data centers have been used for the last 20 years or so. We've been building them up so that we can put databases and then move those that data over the internet from one computer to another. The computing requirements, the work that needs to be done with that data is actually pretty minimal inside these data centers. They don't do that much work. Largely, these things are stored, and there's a lot of heterogeneous workloads within these data centers. They're used by many, many different companies and users. So all of the workloads kind of even out, and you just have this base level of consistent work that happens there. AI factories are fundamentally different in these characteristics. The way AI works, first you have to actually create the AI model. You do that by taking large amounts of data, the examples I was talking about of what you would like the model to do, and you shove it through this supercomputer that does uncountable amounts of calculations. It takes a long time, and it takes a lot of energy and a lot of computing power to do that. And out comes a distillation of all of the knowledge that came in from the raw data into a form that you can use. You can get insights and knowledge out of that. This is exactly like a factory. You put into a factory, an automotive factory, you put in raw materials and energy. All of the raw materials are reconfigured, and out comes a refined product that has far greater value than the inputs.
Yep.
That's how a business works. From an enterprise's perspective, the data centers that we have are largely, they come out of your IT budget, and it's something that you want to minimize. It's just an extra overhead kind of expense. But if you have a factory that is taking something of less value and producing something of greater value, you actually want to maximize that thing. You want to keep operating it 24/7. You want as many of them as possible because you're essentially printing money. And that doesn't come out of your IT budget. That is your OpEx. It's your core business. And so with AI, we have this training part. We also have the part where you actually use the AIs. This is the inferencing part. When you have the model and you deploy them, every time you make a query in ChatGPT or Claude, there's an AI factory somewhere that's taking your prompt and all the data you put in as input, and tokens are coming out, and maximizing the number of tokens you get per unit of energy, per dollar, the uptime of these, minimizing the latency from when you make the prompt till it comes out. These are all the kinds of optimizations and speeds and feeds you would do with a factory. And so that's what we're building, and you can see that they are actually quite different when you look at the designs of them, particularly from a power perspective. With the traditional data centers, you have 10, maybe 15, 20 kilowatts per rack. It's more than sufficient for storing and moving data around. But with a factory, you want to maximize the density as much as possible. The less distance the ones and zeros, those electrons have to travel, the more efficient this machine runs. So we try to pack as much computing as possible into this dense area, but that creates all of these other challenges in terms of powering these data centers. The current generation we have, the Blackwell generation of GPUs, we're at about 130, 140 kilowatts per rack, and we're looking towards going to a megawatt per rack, and that's powering it is one part of the problem, but removing all of the wasted heat is the other part. This thing will catch on fire or melt down otherwise. So we have to switch our cooling infrastructure from air cooling to liquid cooling and do all of these other crazy things. But I think that's super exciting. We now have this great engineering challenge that in power engineering as well as plumbing. Like we have to start really figuring out how to maximize this new domain to produce something that's of such great value, and everybody here can participate in this new industry that's forming.
Very, very well said. And I take your point on the explanation of the AI factory, and I can tell you I myself have tried, and I don't do a good job of that, but we'll all take note of that. But the important point from an ecosystem perspective is the last comment you made, how each one of us in this room can actually play a part in enabling the AI factory for all the benefits of what we are experiencing and will continue to experience, efficiency and more, right? So, again, NVIDIA, I think, like you said, everybody knows about NVIDIA, everybody can pronounce NVIDIA. The name is synonymous to speed and innovation. There must be something inside of the company which is to do with culture and people. How do you do that? How do you remain at that cutting edge of speed, of innovation, and innovation itself?
I think at the root of it, it comes down to what I said earlier, the inception of our company. Instead of deciding what we are going to make, and have that be our defining thing, we decided who we want to work at our company. Our mission to this day is we want the world's best computer scientists to come here to do their life's work, and we really, really mean it. In order to do that, sometimes you have to make some trade-offs and sacrifices that aren't maybe obvious up front. Often we find ourselves in a situation where there's an existing market in computing and technology where potentially we can enter that market and do something in that market better, faster, cheaper than the others that are in there and go compete. And it would make financial sense to do that. But that would violate our mission, because if we are going to have the world's best computer scientists do their life's work, they are not going to stay in our company if all they're doing is rehashing what others have done and doing it slightly better or cheaper. We have to continually find new markets, create new markets, in order to create the conditions by which our engineers, our researchers can innovate. Another part of this is, I just saw a talk or a fireside chat Jensen was doing in the UK when he accepted this award, the Stephen Hawking's award. Yeah. I recommend all of you go watch that. And somebody had asked him a question about something related to this, and he said, initially when he started the company, he read all the books, and there was common sort of ideas on how you should manage people. We had this idea of ranking all your employees, and you should fire the bottom 5% yearly and regularly. And he said over time he figured out all of that, it just doesn't work, and we don't do any of those things, particularly that one. One of the things that you need when you're innovating is you need your people to be courageous enough to go try things that are likely to fail. And if they have a consistent fear that they are going to get fired because they're not performing, because the thing that they took a risk on is too risky, and it's going to look like failure, you don't create a safe space for them to fail, then they're not going to do that. So you have to be committed to that as well. Jensen famously, now it's coming out there, doesn't fire people. We torture everyone until they leave, but we don't actually fire anybody.
Yeah, well, torture was a takeaway for us, I have to say.
Yeah. There's lots of suffering and torture,
but it was also said it is torturing to greatness, right? So I think greatness was the key word. But no, it's very impressive. And again, for all of us as an ecosystem, not just us as a large company, Schneider, but a lot of our friends here, but their businesses, it's interesting to see how you guys have built that culture, which is obviously now leading to the cutting edge innovation. Now, talking about ecosystem, I mean, both our companies are heavily embedded in the ecosystem. I mean, we go to the last GTC I attended was in DC. You speak about all the partnerships you have, and of course we do that. You saw today we bring out a lot of people, but our friends, our customers onto stage, our partners actually. So my question to you was, when you think about our sort of two companies working together, it's been a couple of years now we've been engaging. What's your sense of the collaboration? Where is it at today? And what are the things which you think we should be doing more of, et cetera?
Well, I think it's fantastic. That's why I'm here today.
Yeah. Thank you.
I think our collaboration is already starting to bear fruit. Within our ecosystem and the new ecosystem we're creating around AI factories, Schneider Electric is essential. There's no way we could do this without your participation and your partnership. And for where we need to go, the current technologies that we have is insufficient. The only way we're going to be able to develop everything we need is to work together. Us working together, but not just us. We need a large ecosystem. Fundamentally, we at NVIDIA, we reject this idea that the technology markets are zero-sum and that it's winner takes all. There's the very nature of technology and innovation is that you're creating something new. All of us can contribute something new and add to the world. We don't have to keep taking things from each other. There's so much work that needs to get done, so many things that we haven't done yet. So if we could just align on who is doing what and work together, we can create something much greater than otherwise possible. At NVIDIA, it's kind of funny. We actually don't really have customers directly. We don't sell anything directly. There's like nobody you can come buy something from NVIDIA. Because everything we do goes to market through our partners. We built all of this core technology. We're likely the purest technology company in existence because our product really is just raw technology. By itself, it's not useful. We have to go take our technology, bring it to our partners who then embed it inside their products, in their technology, and then they take it out to market to end customers. Some companies and really work towards their philosophy is to be very vertical, to do everything end to end and own everything in the supply chain so they can own a space completely. The way we look at it, we'd rather just have our tiny part of every industry in every place, and others can come along with us, build on top of us, take our technology, embed it in theirs, and go serve more and more markets. Schneider Electric's a key part of this for us in this space, and not just in terms of going to market, but also we are a customer of your products. We co-develop things together. There's multiple touch points in which we can partner and work together.
Yeah, and we remain cognizant of the amount of work which still needs to be done. I mean, and I think we're all just at the starting point when we think of the AI opportunity. I particularly like that point you made about in the world of technology, it's not a zero-sum game, because we do end up, getting caught up in that. But the size of opportunity itself is so huge that there's enough for everybody to go do. So hence the need for ecosystems to
And the point is that's the very nature of technology innovation. You're creating something new.
Yeah.
If we were not innovating or creating anymore, then it's just a land grab. You're trying to take the same stuff that's been created and take your piece of it.
Yeah.
But the very nature of what we're doing here is always about creating new things. There's always more space.
Yeah. So thank you for that. One other thing, Rev, and every time I go to the NVIDIA offices and see the briefing center and see the innovation there, I'm always so curious about how the world is changing. The last time when we were there a couple of weeks ago in September, your teams shared a lot about the future from an Omniverse, USG perspective, the physical AI, et cetera. Now, of course, you understand this, you run this business, so you know this very well. But just for all of us to understand, tell us a little bit more about Omniverse. Tell us a little bit more about physical AI and how that changes the face of the opportunity, which is already so big, even more in the future.
Yeah, I touched on this a little bit in the first question.
Yeah.
The first deep learning neural net was AlexNet. It was image classification. Yeah. That essentially started the first era of AI from our perspective. We call it perception AI. This is where we created these AIs that were very narrow in scope, very specific, and it was largely about perceiving things. So computer vision, audio, speech recognition, et cetera. Fast forward a few years later, 2017, 2018, the transformer model was created. This opened up the path to GPT. the distinction between this era and the previous one was we now created models by taking large amounts of diverse, unstructured data, basically all the text we could scrape off the internet, shoved it through this supercomputer, and what came out of it was an encoding of all of the rules, all of the laws of language, of all languages that we put through it. And you could use this thing that came out of it, this model, for many different uses. It was very general. And everybody here has probably already experienced this. You could use it to take a small amount of text, like a prompt that says, write me a poem, and I'll write a poem for you. You can take that larger amount of text and change the style, change the poem from a poem into a rap song, change the language. You can then ask it to collapse it into a summary and so on. All of these are very different applications, but fundamentally the same model. We're now currently in the next phase. That phase we call generative AI. We are now in the agentic AI phase, where we're taking these generative models and we are giving them access, a way to sense their environment. The environment for these models are essentially the internet or your computing systems. They can query things there. And we're giving them the ability to take action. So an agent, like a coding agent, could look at your software code base. You can ask it to do something with it, and then it can go execute, go modify the code and go execute on it. Or an agent that can help you book your flights. It could go query all the flights out there. It has access to that database. And then it can go buy the tickets for you or book the tickets on your behalf. So that's the era we're in, and this is a really exciting one. We're not finished with it, but we're now starting to kick off the next era, where we're taking these agents and we're giving them physical embodiments. We're taking them out of the digital world, the purely digital world, and giving them the ability to sense the physical world through sensors like cameras, LiDARs, any sensor. They can then make decisions inside the real world and act in the real world. One such physical AI agent is an autonomous vehicle driver. In some cities in the US, I don't know if they have them here in Vegas yet, but we're seeing the Waymos and others out there. That's essentially a physical AI agent that's doing the driving task. We're starting to create other types of embodiments, humanoids. We already have robotic arms and so on and so forth. Those are showing up in factories and warehouses, in our supply chains, in hospitals, and so on and so forth. This is a very long-winded way to get to what Omniverse is.
Yeah.
Now, in order to build these physical AIs, the brains for the robots that we're talking about here, you need to step back to how we created AI, which is by giving it a whole bunch of examples, a whole bunch of information about the thing that we would like it to do. Well, in the case of the knowledge agents that we're creating, we're somewhat lucky. We have a large corpus of data sitting on the internet. We have lots of text that we could just go mine to go do that. But information about our physical world isn't just sitting around on the internet. We have to gather this information somehow. Gathering this information from the real world, in most cases, ends up being too expensive, both in terms of time and actual cost. In some cases, dangerous. We'd like to have examples of cars. If you're going to make a self-driving car, you would like the driver of this self-driving car to have experienced what it's like when a child jumps in front of the car while it's barreling down the street. We don't actually want to create that situation in the real world in order to gather that information. And so the solution to this problem, we theorized 10 years ago, is instead of trying to get all of the information about the physical world from the physical world, instead let's take the laws, the rules of the physical world, bring it into a computer, and then essentially this simulation we create of the physical world will become a renewable physical data generator. We can generate infinite amounts of data about the physical world, assuming our simulator matches the real world closely enough. And so these physical worlds, these simulations we create, can then be the training grounds for the AIs that are going to operate in our actual world here. The same simulation can also be used to test and validate those AIs. So before you deploy your AI driver out into the road, or the physical AI that's going to be working in your factory, working with heavy machinery, you'd like to make sure that there isn't a bug or a regression in its behavior before you deploy it. So you can use the same simulation to do hours and hours of testing, have it drive millions of miles before you go to deploy that. So to do that, we have to build these simulations, and this requires a lot of computing. Fortunately, the very core of our company from the very beginning has been about simulating physical worlds. We did it for video games, for these fantasy worlds, but we could take those same technologies and restrict them so that they can't do fantasy world things. There's no magical powers and superpowers that you would have in a video game. It has to match the physical world. Once we do that and we accelerate this, we can then use that as a training ground for these AIs and a testing ground for them. That's this collection of technologies to do this simulation, the libraries and SDKs and APIs that we develop with the special algorithms to do this kind of simulation very, very fast on our computers, we call Omniverse. Yeah. This is what we provide to developers such as Schneider Electric to integrate into your offerings. Now, before you can do these simulations, even if you have a great simulator, you have to actually give it the world, the initial state for it to simulate. You need to describe all of the things that are inside that physical world and all of the physical attributes of it for every domain of physics that matters. It's not sufficient to just describe the shape of the things, the geometry. You also have to describe the materials and the material properties. How does light interact with these materials? What is the friction coefficients and restitution and all of the various properties you might care about. And it turns out that there's no one physics simulator, no one algorithm that can do all physics accurately enough and fast enough for everything. Yeah. There will always be many, many different simulators, but we need to simulate these complete worlds with every aspect of it in one place. The only way to really do that is by having a common way to describe the world. Yeah. We need a common representation that all of the tools that we use to design these things inside the world, all the stuff we design around us, the chips, the computers and the systems we design in our AI factories, the buildings and the data centers themselves, the cables, all of that, we need one common place we can put all of that information in so that we can apply these various simulators to them. And to do that, we looked around to see if there was some file format, some representation that's open and common enough that we could build on. And what we found was 10 years ago, Pixar, famous for Toy Story and all those CG movies, had created such a system called OpenUSD, Universal Scene Description Language. And they did it for a similar purpose, for building fantasy worlds, but they had the problem of having many different tools in many different parts of their production pipeline that created all this data that they needed to bring together so that they can build these virtual worlds in common together and feed it through their simulators to actually produce the images in the movie. We looked at it and said, this is incomplete for our needs, but this has the bones of something we can build on and we can keep enhancing that. So we worked for years to keep adding layers and layers of physical properties to it. A few years ago, we finally gathered enough companies to band together to create an alliance of OpenUSD. The founding members were Pixar, of course, Adobe, Autodesk, Apple, and us. And since then, there's been dozens that have joined. And I heard recently that you might be joining as well.
Of course, of course. Well,
Schneider Electric.
Yeah.
I think maybe
Today, actually, we are actually announcing it as we speak right now. So Schneider, including ETAP, including
Yes.
Aviva, we're all joining the
this is great.
Yeah, thank you.
Thank you for joining.
No, but it's you know, the way you explained it, it's so critical. And you said it's a long-winded way to get to the OpenUSD. But the beauty is that when you say physical world, one would imagine humanoids, but it's not just, right? It's your EVs, it's your sensors, it's just so many other things. So that's important for this ecosystem because in some ways we play a role in enabling all that is in the physical world. But the beauty also and comfort is that the physical world is literally getting trained in the virtual world before it's coming into the physical world, right? It's not getting trained in the physical world. That's another big change. But of course, yes, for us, being a part of this alliance is absolutely critical. So
That's right, and it's not just for training. Even without the AI part of this, you know, from the very beginning, simulation has been a core part of what NVIDIA does in order to build and design the complex machines that we build.
Yeah.
We don't know any other way to create our chips, which have billions and billions of transistors. The number of things that could go wrong in it are so great that it's impossible for us to actually design such a chip and ensure that it's actually going to work when we get it back from our fab without doing insane amounts of simulation. From the time I've been at NVIDIA, we've always had this huge supercomputer running 24/7 that puts all of our design engineers our chip engineers on guardrails. Even if an engineer wants to sabotage our chip, they can, because we're continuously testing every single design change to our chip in this supercomputer so that by the time we tape it out, when we send it over to TSMC for them to fab it, we're certain that when it comes back, it's not only going to work, it's going to perform exactly how we simulated it. Yeah. And it's been the case for every chip that we've taped out since I've been there. It comes back and it works the first time.
Wow.
And now with the complexity of the things that we're building, it's not just the chip. We have to design the systems, the rack, the computer is the whole AI factory. Mm-hmm. All of this has to be co-designed together. We have no chance of being able to create these things if we don't simulate it all holistically and co-design it all together. Awesome. The complexity of all of the things we're building in the world are now approaching the complexity of our chips. You can't build a factory or a warehouse with the software and automation and the robots and everything else in there and make sure that it's going to work right when you build it without simulating it in the design process first. That is the only way we're going to be able to achieve it. Otherwise, we're gonna build a whole bunch of things that don't work, and we're gonna waste a lot of material, energy, and time rebuilding them in the real world, trying to modify and change them in the real world, and likely these things will just fail and we'll hit a ceiling. Yeah. It is impossible to build our computers with this complexity without simulation, and now everything else we're building in the world, as it gets infused with computing, is the same complexity. Yeah. So it's really critical that we do this, and we all do it together.
Very well said. And look, we're coming to the end of our time. You know, this discussion is obviously great, and sometimes it can get super technical, but I also want to remind all of us that we are here because we play a role in this world of technology. It's not just enough to be a generalist anymore. You need to be detailed if you have to play a part in this ecosystem, right? So thank you for sharing and the insights. Maybe just quickly in the last 1 minute, what else do you think we could do better together in this collaboration for Schneider Electric?
Our collaboration so far has been great, but I think the biggest challenge we're going to have is You know, in the keynote, I heard that basically this industry hasn't changed much for 70 years. The last time we had a major revamp to building power, building the grid and all of the power infrastructure was 70 years ago, and we've reached the limits of that. I imagine that this industry no longer has the same muscles, the muscle memory to move quickly and iterate quickly on new ideas and new techniques. I think this is something that we have to consciously change. We're at a critical point here. This industry has to align with how we work in the computing and tech industry and try to work at our pace by moving quickly and failing quickly.
Yeah. Very good. Well, so it's, first of all, thank you. Should I say on the part of the ecosystem that challenge accepted? Should we? Yeah, we should. Yeah. Look, really, thank you, Rev, for sharing all what's happening in the world of AI. And I hope this session was insightful. But again, remember the points which we are making, the key points being that this is not a zero-sum game. The size of the opportunity is so big that there's enough for all of us to play in. Secondly, we need to go deep into technologies. These sessions can sometimes be hard, but just being a generalist is not going to cut it, at least if you're in this room, right? And there is so much more to look forward to, and we're just scratching the surface with agentic. And this whole world of physical AI brings an opportunity for everybody, again, in this whole ecosystem. So thank you again, and thank you to all of you for coming back for the session. Thank you.
Thank you, everyone.
Okay, well, thank you so much. Great.